Newton's third law says that when one body exerts a force on a second body, that second body will simultaneously exert a force equal in magnitude and opposite in direction on the first body. It can be written in vector form as the force of A on B is equal to the negative of the force of B on A. Let's try it with two blocks A and B. Alex is asked to move two boxes of books in contact with each other and resting on a frictionless floor. He's going to move them at the same time by pushing on box A with a horizontal force of 9.5 newtons. Note that his push is only on A because that's what he's in contact with, and then A in turn will push on B. Box A has a mass of 10.5 kilograms and box B is 7 kilograms. Alright, one of the first things we want to do with a problem like this is decide what system we want to analyze. It's our decision what blocks are included in the system. The first time I do the problem, I'm going to let all the mass be the system. So my dashed boundary goes around both A and B. I'm going to treat it as a 17.5 kilogram system. Now, what is the system in contact with? Well, there is a normal force from the floor. There's a force of gravity, which would be a non-contact force. And there's also the person who's pushing. The person pushes with 9.5 newtons. So, from Newton's second law, we can find the acceleration of the system. I'll let the net force be Alex's push. It's 0.543 meters per second squared. Alright, now here's where it gets interesting. We're going to cut the system up into two blocks, and we'll just focus on one of them now. But the question is, which one is easier to analyze, A or B? The answer is B is actually going to be easier to analyze because there's only one force acting on it that's in the horizontal direction. But who supplies that force? Well, it's not Alex because Alex is not in contact with block B. Alex pushes on block A, and block A in turn pushes on block B. So I'll do a free body diagram for B. And this is going to be the force of A on B. That's going to become the net force acting on B. So then you might be wondering, well, what forces act on block A? And this is where Newton's third law comes into play. If box A pushes on B in the forward direction to the right, then box B has to push back on A with the same magnitude but opposite direction. And this will be the force of B on A. And that's not the only force acting on A, though. Another force that acts on A is the push from Alex. Alex pushes with 9.5 newtons. I'll call that FP. And those are the forces that are important for block A. There's also, of course, a weight and a normal force, but they don't matter to this situation because they're going to cancel. Now let's find the force that's exerted on mass B by mass A. Alright, so we already have the acceleration of the whole system, and we can use that to find the net force on B. All we have to do is rewrite Newton's second law. The net force on B will equal the mass of B times the acceleration. So the mass of B was 7 kilograms. Acceleration is 0.543. So this is a net force of 3.8 newtons. And yes, it's the net force on B. But that is also the force of A on B, because A is the only thing in contact with B that would push it horizontally. Alright, so let's go ahead and label some of these force values then. The force of A on B is 3.8 newtons. And that means that the force of B on A is also 3.8 newtons. But remember that the force of push was 9.5 newtons. So even though Alex applies 9.5 newtons on block A, only 3.8 newtons end up being used to accelerate block B. The reasoning behind this is, see, Alex has to accelerate the whole system. But block A only has to push the smaller block B, and that's why less force is required in order to achieve the same acceleration. Now, is there another way of calculating this? Yes, there is, and it comes from the same principle that guided the cart and hanging mass scenario. To see the analogy, what you might do is imagine that the blocks were reversed. And instead of being connected by a contact between surfaces, let's say they were connected by a string. So this is block A and this is block B. Now Alex only pushes on block A. So in the analogy, he is like the gravity that is applied to the hanging mass. See? So he pushes this way with 9.5 newtons on the hanging mass. His push doesn't get applied to block B, but a force gets applied to block B nevertheless through the cable instead. If we were to do this problem, the calculations would be the same. The force of the cable here would be 3.8 newtons. What does this tell us? It tells us that the formula that we had used in the past for hanging mass situations will actually also apply here. In the analogy, mass B is like the cart. It's being pushed by the object that Alex is actually in contact with. With that in mind, we should be able to find the force of A on B by using the mass of the cart divided by the mass of the system and then multiplying that by the force that Alex is pushing with. Next, let's put Alex on the other side of this system and see how things change. Now he'll push from the right side. He'll apply his force directly to mass B, which is the smaller mass. Do you think the normal force of B on A will be different from before? Well, we can calculate the normal force quite easily using the formula force of B on A equals the fraction of the cart mass divided by the total mass times the magnitude of his push, which will again be 9.5 newtons. Here we see that the force of B on A becomes 5.7 newtons. And this means that A will push back on B with 5.7 newtons too. So what accounts for the difference here? Like, why is it only 3.8 newtons when B is the cart, but when A becomes the cart, now the force is 5.7 newtons? The reason why is Alex applies his force on the edge of one of the boxes. He's responsible for pushing all the mass, so it takes 9.5 newtons to do that. Now, since a large majority of the mass here is concentrated in block A, block B has to push pretty hard to accelerate A with the same acceleration that B had before. It's going to be 0.543 meters per second squared in both cases. So when we make a cut in an object that's closer to where the force is applied, then the normal force between those surfaces will be larger. If we make a cut that's farther away from where the force is applied, then the normal force between those blocks there does not have to be as large.